Have you ever stopped to think about how incredible language is? Seriously. With basically zero effort, we take these abstract thoughts, turn them into sounds, and then someone else's brain just decodes them. It's magic. It's one of the most amazing things we do as humans. But how in the world does it actually work? Well, that's what we're going to get into.
It all starts right here, inside our heads. And I love this quote because, let's be honest, it's easy to think of the brain as just, well, a messy glob of goo. But it is so much more. Our understanding has just skyrocketed, and we now know this 3-pound organ is a computational powerhouse beyond anything we've ever built.
So that leads us to the big question, right? How does this thing manage to create poetry, write novels, or even just let us have a simple conversation? Well, it turns out neuroscientists discovered something really clever. To understand a masterpiece, sometimes the best thing to do is study what happens when it breaks.
Think about it. If you want to figure out how a complex machine works, a pretty good strategy is to see what happens when a single part fails. That's exactly how we got our first real clues about how the brain handles language. Our story really kicks off in 1861. A French physician, Paul Broca, had a patient named Leborn. Now, Leborn was fascinating because he could understand everything you said to him, but for years, he could only say one single syllable, tan. That's it. So everyone just called him Tan. After Tan died, Broca performed an autopsy, and he found a very specific area of damage, a lesion on the left side of his brain. This was a huge deal. It was the first real physical link between a piece of the brain and a specific human ability. And here's the crucial takeaway. Broca connected that specific damaged part of the brain, which we now call Broca's area, to a very specific job, producing speech. This condition, Broca's aphasia, is defined by this struggle. The patients know exactly what they want to say. The idea's in their head, clear as day. But the words, they just won't come out right.
Now, this is where it gets really interesting. Just a little while later, a German neurologist named Karl Wernicke found patients with the complete opposite problem. They could talk up a storm fluently with perfect grammar, but it was all complete nonsense. And, this is key, they couldn't understand what other people were saying. This contrast was a bombshell. It showed that language wasn't just in one spot. It had at least 2 specialized centers doing very different jobs.
This table really paints a picture of just how bizarre Wernicke's aphasia is. The speech flows perfectly, but the content is often called jargon or word solid. They might swap out sounds or even invent completely new words and have no idea that what they're saying is just incomprehensible. Wernicke tied this to damage in a different spot, now called Wernicke's area. So, boom, now we've got 2 pieces of the puzzle, one area for making speech and another for understanding it. For a long time, that 2-spot model was pretty much the whole story. But as you can probably guess, it turns out the brain is way more complicated than that. It's not just about the spots themselves. It's about how those spots talk to each other. And this is the piece of evidence that blew the old model up: conduction aphasia. The amazing part is, Wernicke actually predicted this could happen. He asked, what if Broca's area is fine and Wernicke's area is fine, but the wire connecting them is cut? The result is a patient who can understand speech and can speak their own dots just fine, but they cannot repeat back what they just heard. It was definitive proof that the connections, the brain's information highways, are just as critical as the cities they connect. This all brings us to how we think about it today, which is called the dual stream model. And it's actually pretty intuitive when you break it down. Your brain basically has 2 parallel pathways running at the same time. The first is the ventral stream. You can think of it as the what stream. It hears a sound and figures out what it means. That's your comprehension system. Meanwhile, the dorsal, or how stream, is figuring out how to make those sounds with your own mouth. That's your production system.
Okay, so we've gone from a couple of spots on the brain to this complex, interconnected network with multiple pathways. But how can we actually see all of this happening inside a living, working brain?
Well, the answer came in the early 1990s, and it was an absolute game changer: functional magnetic resonance imaging, or fMRI. What this technology lets us do is see which parts of the brain are lighting up with activity when someone's doing a task, like listening to a story, just by tracking the changes in blood flow. And when I say it was a game changer, I am not exaggerating. The impact on neuroscience has been, well, just look at this number. This chart really says it all. The decade of the brain in the 90s was really just the warm-up act. Today, more than 2,500 fMRI studies are published every single year.
It has given us this incredible window into how the mind actually works.
But here's what's so cool. We haven't thrown out the lessons we learned from patients like Tan. We've actually put that approach on steroids with a technique called VLSM. Imagine this. Researchers take the brain scans from hundreds of patients with different kinds of brain damage, and they digitally stack them all on top of each other. Then a powerful computer goes through the brain, tiny little cube by tiny little cube, they call them voxels, and it asks a simple question. Do the patients with damage right here have more trouble with a specific task than the patients who don't have damage here? By doing that over and over across the entire brain, this stunningly detailed functional map just emerges. It's basically Broca's original idea, but scaled up with incredible precision.
All right, so let's pull all these threads together. After this journey from the 1800s to the high-tech labs of today, what have we learned? What does the modern map of language in the brain actually look like?
So here's the big picture. First, language isn't in one or two little spots. It's a huge, sprawling network spread across the brain. Second, within that network, different neighborhoods have very specialized jobs. Third, the connections, those white matter highways, are every bit as important as the processing hubs themselves. And finally, and maybe this is the most important insight of all, we figured out how this masterpiece works by carefully studying its failures, which in turn revealed the beautiful design of the whole system.
And that all leaves us with one last really big question to chew on. We've just seen that the system we use to build and express our thoughts is this complex, distributed network. So what does that imply about our thoughts themselves? About our consciousness? Is that a network too? That's a question neuroscientists are still working very hard to answer.